Hey Data Junkies, welcome back. I'm your host Shawn Janzen, and we're continuing our introduction into the correlations here. In the previous video we talked about some foundational topics. In this video here we're going to be talking about how we can calculate covariance and the correlation coefficient, and in future videos we're going to be replicating these things in R and taking this out to the whole next level here. So let's get started with covariance. Now with covariance we're talking about how we can measure these relationships in terms of, well, with the correlations in general, to see how they increase, decrease, or stay the same. And so when we're dealing with this, we need a measure called covariance. Covariance is talking about deviations from the mean. If both of them are deviating from their means by a similar amount, they're more likely to be related, and so their covariance reflects this. Let's go ahead and take a snapshot here of a sample I put together where we have the number of ocean hashtags about environmental topics somebody's used on Twitter. You can think of these things such as the amount of plastics in the ocean, or the effect of climate change on local beachfront areas and things like that, or some animal rights activism thing that might happen to be oceanly related. Contrast that with the number of environmental causes somebody supports online in general. And if we looked at these as how many you might have done over the past month, we've got 5 different participants that have given us their information in the leftmost column. And participant number 1 has done 5 different ocean-related hashtags on Twitter this month and supported 8 different other causes online in general. Person number 2 has done 4 ocean-related environmental hashtags on Twitter and 9 other causes on environmental topics in general, and so on for our 5 participants. I've taken the mean of each of those, 5.4 and 11 respectively, and the standard deviation of both of those, 1.67 and 2.92 respectively. And on the right side of the plot here, I've sort of put out these data points where on the x-axis we have our individual participants, and I've plotted their points on the y-axis for both the number of ocean hashtags on Twitter they've used and the number of causes online that they've supported. I have horizontal lines cutting across in both green and blue, where green is the mean for the causes and blue the mean for the ocean hashtags. We have red dotted lines extending from each observation point to the respective means, and those red dotted lines, that's an amount of error. How far each point is from their means is a measurement of error, and I have next to the data points a number that kind of gives us a perspective of how far that error is. Now, when we're talking about variance and covariance again, I want to just kind of remind ourselves about variance, that the variance itself says how far do they deviate from their means by a specific variable. And we're closely linked with these sums of squares to get an idea of these, because otherwise it'd cancel out and go to 0. Covariance is similar to variance. We're talking about how much they deviate from their means, but we're talking about how it happens with 2 variables at the same time. Where variance only looked at 1, covariance looks at 2. So let's go ahead and see a little bit on how we get this done. We have 5 steps that we can use to calculate covariance. First of all, we look at the error between the mean and the subject's score on the first variable, the x variable. And then we do the exact same process again, but for the second variable, y. We look at these mean differences and we multiply them together in the 3rd step, following in the 4th step by adding up these multiplied mean differences, and that gives us what we call the cross product deviation. We take the cross product deviation and we go ahead and divide up, and that's going to give us our covariance. So let's see this, how it looks mathematically. On the top here I have the variance function, which is the sum of the x observations minus their x means squared. And in the covariance function, it's very similar, but instead of doing the x minus x bars squared, we're doing x minus x bar times y minus y bar. And we're not squaring either of them. We don't need to square the x minus x bars because we have a second variable here, and those are getting multiplied together instead of doing a squaring. And both in the denominators, they still have the n minus 1. So let's go ahead and see how this looks in practice. I'm using the same data here from the number of ocean hashtags and the number of online causes. And so in the green, I have the ocean hashtags circled, and it has a mean of 5.4. So I'm going to take each one of those values. 5 minus 5.4 gives me negative 0.4. And if you look over in the numerator of the long line there of different values, the first one is negative 0.4. Look across to its matching partner there on participant number 1 with 8 online causes minus its mean of 11 gives us a difference of -3, and that's the first value there next to -0.4. So we have both our ocean and cause variables, both of them by one participant. They're getting subtracted by their respective means, and they're getting placed up in the numerator next to each other. Let's look at the next pair of -1.4 and -2. Looking at participant number 2, he or she has had 4 online ocean hashtags minus the mean of 5.4. That's where we get that -1.4. And then we have the number of causes that were 9 minus the mean of 11 gives us -0.2. That's where those two numbers come from. And we continue across for every participant in that particular data set. So we have 5 different differences. They're all getting multiplied together. Then we add all those multiples together, and that gives us 17. In the denominator, we had n-1, which comes to 4. So we've got 17 over 4. Divide that, we get a covariance of 4.25. Now keep in mind, just like variance, covariance itself, it's not an easy number to interpret. We just have to know that it is talking about the amount of variation by 2 variables on how much they're agreeing and their amount of variance with each other. So keep in mind that when you're dealing with covariance, that's fantastic, but it has some disadvantages. One of the problems is that it depends on its units of measure. These are not standardized measures. So if you have, let's say, a covariance in miles, and you want to go ahead and convert it to kilometers, the covariance function changes as well. Well, the covariance function doesn't change, but the covariance number reported does. So if we were to convert this to kilometers, our covariance of 4.25 is now an 11. So if you're dealing, let's say, with an analytics team at different points in the world and you're on different units of measure, this could cause a little bit of problems. So one of our ways to deal with this is to standardize covariance. And how do you standardize it, ask? I'm glad you ask. I'm going to tell you. You standardize it by dividing by the standard deviation of both variables. You need the standard deviations for both your x and your y, in this case your oceans and your causes. And when you do that, it changes from covariance into what we call the correlation coefficient, or R. And so when you do that, we're stripping away the units of measure, and so it's unaffected by such differences. So let's go ahead and calculate the correlation coefficient, knowing what we just said. I'm going to use this exact same data here. I have the full function up on the screen for you, but I also have a shorter version of that function. That full function is the covariance function, but I've added in standard deviations for x and y. And so what we now need to look at here is that the shorter version, we already had the covariance of 4.25. All we need to do is divide it by 1.67 and 2.92. That's going to give us an R function, an R value of 0.87, which is a strong, very strong, positive correlation. There's a strong relationship here between the number of ocean hashtags people are using on Twitter for environmental causes and the number of online causes for other things they're supporting in general. And if I want to go ahead and see, is this a significant correlation, then we need to start talking about p-values. Remember, we can talk about R in terms of its effect sizes and how strong of an effect it has, but that's substantive. If we want statistical, then we need to turn to our p-values. So in order to figure this out, R uses a t distribution. It tracks out across the t curve. And in order to get t when you're coming from R, we have a different function. This is not a t-test like you saw with the samples of mean t-tests and whatnot, but the t distributions are used for lots of different ways to calculate things out. So this is just one way of getting another t value. And so when we're doing it in the context of R, in the numerator we have R times square root of n minus 2 divided by the square root of 1 minus r squared. And with that we can also use n minus 2 degrees of freedom. Once we have degrees of freedom and a t-score, we can figure out if we're statistically significant. So in this case, if we wanted to see the correlation between the ocean hashtags on Twitter and general online support for causes, we have an R of 0.87 and an n equals 5. Let's go ahead and use an alpha of 0.1 because we've got a really tiny sample and see if we're significant. So I take that function to find t, I plug in my values, and that's going to, when I bring out the math, come out to 3.06 rounded with 3 degrees of freedom. Now, if I would have already looked up on a t-table or used a t-calculator, like perhaps an R with the qt function, I would know that my t-critical value for a two-tail test is approximately 2.35. At this point, I can already see that the t I obtained is larger than my t critical, and so I'm statistically significant, and I can move on. I can say I can generalize my findings, reject the null, etc., etc. But if I want to get a little bit more specific, I need to go to the t-table itself, or use a function in R, which we're not using in this particular video here. So looking at the t-table, I'm going to bring it up, and here's your snapshot, and then I'm going to isolate out the degrees of freedom row for equals to 3. So I'm looking at degree of 3, and then I look across, track the numbers going across, and find which value does my t obtained most closely relate to. So I track it across, and I find that my t obtained of about 3.06 falls somewhere between that t critical I had of 2.35 and 3.18. It's a little closer to 3.18, but it's still between the two. So I know I'm in between those values there. I'll look up the t-table, and I find, since I'm doing the two-tailed test, I'll look at the alpha scores for those. So I know my p-value of a t with 3 degrees of freedom is 3.06, is somewhere between the values of 0.1 and 0.05. I'm not sure exactly, since the t-table here, at least this particular one, doesn't get much more finite and granular than that, so it's just giving me a range of where my actual p-value is at. So I can say then that I'm still statistically significant at alpha of 0.1, but not at alpha of 0.05. So let's go ahead and report this up in an APA style format. So the way I say this is the number of ocean environmental hashtags used on Twitter was significantly correlated with the number of general environmental activities, with R equals to 0.87, P is less than 0.1. Now I don't have to say that they were Pearson's R significantly correlated, because in my statistic I'm saying R is equal to 0.87. So the reader should be able to infer that R is Pearson's R in this particular case. If you really feel the need to express it, you can. Just try not to be too redundant. And in this case, I'm using P is less than my given alpha, because I don't have an exact p-value to report. And with that, that's going to close up on how to do this by hand. I'll see you all in the next video, where we talk about doing this in R.